Electrical grounding involves more than just the jumper at the meter. There are multiple grounding points within an electrical system. Firstly, the meter socket itself has a grounding terminal. The jumper you mentioned connects to this grounding terminal. This terminal is typically connected to a ground rod or, in some cases, a water pipe via a grounding wire. Secondly, a ground rod is a metal rod driven into the ground to provide a low resistance path to the earth. It's connected to the grounding terminal on the meter socket or directly to the electrical panel. Thirdly, a cold water pipe can be used as a grounding point. However, this method is generally considered less reliable than using a ground rod due to the possibility of non-conductive couplings or repairs in the water pipe. Fourthly, the main electrical panel in a building also has a grounding terminal that's connected to the ground rod or water pipe. Finally, electrical outlets and appliances have a grounding prong. This prong connects to a grounding wire within the electrical circuit, and that wire is ultimately connected to the grounding terminal in the electrical panel. The purpose of grounding is threefold. Firstly, and most importantly, safety. Grounding provides a low resistance path for electrical current to flow to the earth in the event of a fault. This prevents the current from flowing through people or equipment, thereby helping protect against electrical shocks and fires. Secondly, voltage stability. Grounding helps to stabilize voltage levels within the electrical system, preventing voltage spikes or drops that could damage equipment. Thirdly, noise reduction. Grounding can help to reduce electrical noise and interference in electronic devices, leading to better performance and reliability. Ensuring proper grounding in an electrical system is essential for safety and optimal performance. This includes using a ground rod, connecting all grounding points together, and regularly checking the grounding system for continuity to ensure that the low resistance path to ground remains intact. The grounding conductor, often green or bare copper, provides this essential path. It's important to distinguish between grounding and bonding. Grounding connects the electrical system to the earth, while bonding connects various metallic parts of the electrical system together to ensure they are at the same electrical potential. This helps to prevent voltage differences that could create a shock hazard. Consider the scenario of a metal appliance. The grounding conductor connects the metal chassis of the appliance to the electrical panel's grounding bus. If a fault occurs within the appliance causing a live wire to come into contact with the chassis, the grounding conductor provides a low impedance path for the fault current to flow back to the source. This high current flow will trip the circuit breaker or blow the fuse, quickly disconnecting the power and preventing a dangerous shock. Without proper grounding, the metal chassis could become energized, posing a significant risk of electric shock to anyone who touches it. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. It specifies the minimum size of grounding conductors based on the size of the circuit conductors. It also outlines the acceptable methods for grounding electrodes, such as ground rods and water pipes. Proper grounding also contributes to surge protection. When a lightning strike or other surge event occurs, the grounding system provides a path for the surge current to dissipate into the earth, protecting sensitive electronic equipment from damage. Surge protective devices, or SPDs, are often installed at the service entrance and at downstream panels to further enhance surge protection. These devices divert surge current to ground, limiting the voltage that reaches connected equipment. Grounding also plays a role in electromagnetic compatibility, or EMC. A properly grounded system can reduce the emission of electromagnetic interference, or EMI, from electrical equipment. This is important in environments where sensitive electronic equipment is used, such as hospitals and laboratories. The grounding system acts as a shield, preventing EMI from radiating into the surrounding environment. Regular inspection and testing of the grounding system are crucial to ensure its effectiveness. Ground resistance testing can be performed to verify that the ground rod is providing a low resistance path to earth. Visual inspections should be conducted to check for loose connections, corrosion, and damage to grounding conductors. Any issues that are identified should be promptly corrected to maintain the integrity of the grounding system. In addition to ground rods and water pipes, other types of grounding electrodes may be used, such as ground plates and concrete-encased electrodes, often referred to as UFA-grounds. Ground plates are buried metal plates that provide a large surface area for contact with the earth. Concrete-encased electrodes consist of a length of bare copper conductor encased in concrete. These electrodes are often used in new construction to provide a very effective grounding system. The size and type of grounding electrode required will depend on the soil conditions and the local electrical codes. It's important to consult with a qualified electrician to determine the appropriate grounding system for a particular application. The connection between the grounding electrode and the grounding conductor must be made with a listed connector. This ensures a reliable and corrosion-resistant connection that will maintain its integrity over time. The grounding conductor should be protected from physical damage. If it is exposed to mechanical stress, it should be installed in conduit or otherwise protected to prevent it from being broken or damaged. In some cases, a separate grounding electrode conductor, or GEC, is required to connect the grounding electrode to the electrical panel. The size of the GEC is determined by the size of the service entrance conductors. It must be large enough to safely carry the fault current back to the source. The grounding system should be designed to minimize ground loops. A ground loop occurs when there are multiple paths to ground, creating circulating currents that can cause noise and interference. To minimize ground loops, it's important to connect all grounding points to a common ground bus. In sensitive electronic equipment, isolated ground receptacles may be used. These receptacles have a separate grounding conductor that is isolated from the building's grounding system. This helps to reduce noise and interference in the equipment. Grounding is not only important for safety and performance, but it is also required by electrical codes. Failure to properly ground an electrical system can result in fines and penalties. It can also void insurance coverage in the event of a fire or other electrical incident. Therefore, it's essential to ensure that all electrical work is performed by a qualified electrician who is familiar with the applicable codes and standards. In industrial environments, grounding is even more critical due to the presence of heavy machinery and electrical equipment. The grounding system must be designed to withstand the high fault currents that can occur in these environments. Special grounding techniques, such as equipotential bonding, may be required to minimize the risk of electric shock. Equipotential bonding involves connecting all metallic parts of the electrical system together to ensure they are at the same electrical potential. This helps to prevent voltage differences that could create a shock hazard. In hazardous locations, such as those where flammable gases or liquids are present, grounding is especially important to prevent the accumulation of static electricity. Static electricity can ignite flammable materials, causing an explosion. Grounding helps to dissipate static charges, minimizing the risk of ignition. The NEC Article 250 provides comprehensive requirements for grounding and bonding electrical systems. This article covers a wide range of topics, including grounding electrodes, grounding conductors, bonding jumpers, and equipment grounding. It's important to consult this article when designing or installing an electrical system to ensure that it meets the applicable code requirements. The grounding system should be designed to accommodate future expansion. As new equipment is added to the electrical system, the grounding system may need to be upgraded to ensure that it can handle the increased load. It's important to plan for future growth when designing the grounding system to avoid costly modifications later on. In summary, grounding is a critical aspect of electrical safety and performance. It provides a low resistance path for fault current to flow to earth, preventing electrical shocks and fires. It also helps to stabilize voltage levels, reduce noise and interference, and protect against surge events. Proper grounding requires the use of a ground rod, connecting all grounding points together, and regularly checking the grounding system for continuity. It's essential to consult with a qualified electrician to ensure that the grounding system is designed and installed in accordance with the applicable codes and standards. Remember to always energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as insulated gloves and safety glasses. Working with electricity can be dangerous, so it's important to take all necessary precautions to protect yourself from injury. The size of the grounding electrode conductor, or GEC, is typically determined by NEC Table 250.66. This table provides the minimum size of the GEC based on the size of the ungrounded service entrance conductors. The GEC must be sized to safely carry the maximum fault current that could occur on the system. The grounding electrode system should be inspected annually to ensure that it is in good condition. The inspection should include checking the condition of the ground rod, the grounding conductors, and the connections. Any signs of corrosion or damage should be addressed promptly. The grounding system should also be tested periodically to verify that it is providing a low resistance path to earth. Ground resistance testing can be performed using a ground resistance meter. This meter measures the resistance between the grounding electrode and earth. The resistance should be below a certain threshold, typically 25 ohms, to ensure that the grounding system is effective. If the resistance is too high, the grounding system may need to be improved by adding additional ground rods or by improving the connections. The grounding system should be designed to minimize the risk of touch potential. Touch potential is the voltage difference between 2 points that can be touched simultaneously. If the touch potential is too high, it can create a shock hazard. The grounding system can be designed to minimize touch potential by bonding all metallic parts of the electrical system together and by providing a low resistance path to earth. The grounding system should also be designed to minimize the risk of step potential. Step potential is the voltage difference between 2 points that are a meter apart. If the step potential is too high, it can create a shock hazard. The grounding system can be designed to minimize step potential by using a ground grid or by burying grounding conductors in the earth. In addition to grounding the electrical system, it is also important to ground electronic equipment. Electronic equipment is sensitive to voltage fluctuations and noise. Grounding electronic equipment can help to protect it from damage and improve its performance. Electronic equipment should be grounded to a dedicated grounding conductor that is connected to the electrical panel's grounding bus. The grounding conductor should be sized according to the manufacturer's recommendations. In some cases, it may be necessary to use a shielded grounding conductor to reduce noise and interference. Grounding is an essential part of electrical safety and should not be taken lightly. It is important to understand the principles of grounding and to follow the applicable codes and standards. If you have any questions about grounding, consult with a qualified electrician. They can help you to design and install a grounding system that meets your needs. Always remember to prioritize safety when working with electricity. Turn off the power before working on any electrical equipment and use appropriate personal protective equipment.